Okay, so today we begin a new chapter, chapter 4, which is more application of derivatives. So you might recall at the beginning of the semester how we talked about many ways in which calculus differs from algebra, all the limitations we have in algebra that we were not able to get certain pieces of information without the use of calculus. Yes.
Is this going to be on the...
No, that's 4.1. I think it's up to Friday's material, right? 3.10. Well, so one of those pieces of information about functions, or properties, is how we find the maximum or a minimum of a function. And so without calculus, we would have made a table of values of x to obtain those values of y for a different interval. So you will notice how, number one, those values get smaller and smaller all the time to then get bigger and bigger every time and eventually reach a minimum value. And even if you do infinitely many values, you may run into the situation in which you may not get the exact maximum or minimum. So in this case, in this chapter rather, we are going to use calculus to find those maximum and minimum values for this function. So we have these definitions about absolute maximums and minimums and local maximums and minimums. So these are the official definitions, the algebraic definitions, if you will. But I think it would be better if we look at this using some graphs right here. So the definitions are there, but the thing is, the only difference between absolute and local is that of the absolute being the actual largest of the maximums. Because if we look at a function, for example, a function may have more than one maximum at some close interval, and but which one would be the largest? Which one is the absolute maximum? The absolute maximum is the largest of the maximum, and at the same time a function may have more than one minimum value at some closed interval. So the lowest value is actually the absolute minimum. So that's the difference between local and absolute. So let's have a look at some graphs. Okay, so suppose we have this graph right here. Let's identify the maximum values for now. Well, so notice these functions have maximums. It has a few maximums, and they're defined on a closed interval, not on an open interval. So in this case, well, let's circle those maximums. So this is one of the highest points on the graph. That's one of the maximums. We have another maximum here. You know how the graph goes from increasing, reaches a maximum point, and then starts to decrease. And we have another maximum point, if you will, even though, well, it's not defined. So I'm not going to include this value because it's ultimately not defined at that point. So those are the maximums. Let's label as a maximum. And also, this is another maximum. Let's label the minimums. Well, so this is a minimum point. It's right here. So that's one of the lowest points on the graph. But there's another minimum right here. However, notice how at x equals to 2, the function has a little hole in here. So even though it's going decreasing and then increasing, which would tell us that the graph it has a minimum in this case. Well, notice this point in the middle of nowhere, that's actually going to be the minimum. Now, we need to identify these points, these maximums and these minimums, as local or absolute. So let's do one at a time. For the maximums. For the maxima right here, well, this maximum is smaller than that maximum. Do we agree with this?
Yes.
So this means this is the absolute maximum, and this is just some local minimum or relative minimum or local or relative. All right. Now let's have a look at the minimum points. This one right here, which is the lowest point on the graph, that's actually the absolute minimum. And in this case, well, the other minimum right here, which is not the lowest point in the graph, but still is described or regarded as one of the minimum points, it's going to be the local or relative. Local or relative minimum, all right? So that's how we describe these minimums, local or absolute. All right, what about this function in this case? Well, so it looks like a cubic shifted 1 or 2 units up. Well, in this case, it turns out that there is really no maximum. It just grows and goes on forever to positive infinity. So in this case, no maximum, no max, no min. It's just a function that increases. It's just increases. Nevertheless, in this case, this function contains a point of inflection. That is, when the graph changes its orientation from concave down to concave up. But that's something that we're going to look at later in the chapter when it comes to the second derivative test. That's for concavity, and that's another very important property of functions. What do we have here? The sine function. Well, this sine function, let's identify the maximum points. Maximum, 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 minimum, minimum, minimum. And well, if the pattern continues, you know, as it is the periodic shape or the periodic property of the function, well, it's going to have minimums in this case at minimum at x at y equals to -1 and maximum at y equals to 1. All right. So if we restricted the domain of this function to, I don't know, say pi over 3 to, well, I mean pi over 6 to, I don't know, to pi, for example, or 3 pi over 2, well, in this case, we would have this as our absolute maximum, this will be our absolute minimum, and this will be our relative max and relative min in this case. But well, in this case, we're not restricting. We're just observing how, in this case, trigonometric functions behave, in particular the sine and cosine function, which just oscillate between -1 and 1, being the negative equals y equals -1, and being the maximum y equals to +1. All right? Okay, let's have a look at more pieces of information here. The extreme value theorem. Okay, before looking at the extreme value theorem, so it's important to note that these values right here, where the maximum occurs, for example, in this case, x equals to 3, that's the value of x in which the derivative, that is, if we trace a slope, I mean, if we trace a tangent line, the slope of that line would be 0, all right? And these numbers that make the derivative equal to 0 are called critical numbers. We would also have a critical number here, another critical number there. I believe this critical number would be at x equals, is that a pi over 2? Pi over 2, 3 pi over 2. Those are the critical numbers in this case, but well, we're not going to look at these critical values just by looking at the graphs. In fact, we're going to look at the algebraic process to go about these critical values. All right, and that's the extreme value theorem.
If the critical number is just the center of the middle of the graph, or what? Can you repeat what you said?
So So the critical values are the values that make the slope of the tangent line equal 0. In other words, the derivative equal to 0. And this is key when determining those algebraically, right? So this is the graphic approach to that. Then let's look at the algebraic approach to this. All right. So, well, we're not going to look at these critical values just yet. So let's keep looking at some of these maximum and minimum values and determine their nature, whether these are absolute max, absolute mins, you know. So, okay, this would be a max. This would be another max. And this one would be a min. And this is another min. But again, we need to identify whether from those two maximum points, which one is the absolute maximum and which one is the absolute, the relative or local maximum. In this case, the highest of them, this is the absolute max, and this is the relative max. And well, between these two means, well, they look close to one another into their values of y. However, this one is still below this minimum, so that's our absolute mean, and this is just a relative mean. Let's look at another graph and determine whether, in this case, this is a max. And actually, it's only one maximum point, so that's simply the absolute max. Over here we have the relative min, and this is the absolute min. Because look at the values of y related to these 2 points. This one is a lot, well, somehow smaller than this one y value. That's what makes it an absolute mean, the lowest of them versus the relative mean, which is slightly higher, but still it's located at a lower point. All right, what do we have here? All right, so max, and well, we have a min, and min. All right, these two maximum points, seem to be the same maximum point, and there's no other maximum points other than those two in this given interval. So in this case, they are both absolute max, and between the minimums, these two means are pretty much the same. This is relative minimum, and that's because this minimum right here, it's even below those two relative minimums, which makes it the absolute minimum. So depending on the behavior of the function, we may end up with only one maximum point or more than one maximum point that happens in that case be the same value. That's actually also the absolute, is the absolute maximum. And like in this case, we have different minimum points. 2 of them happen to be the relative minimum, but the smallest of them will be the absolute minimum. So right now we're looking at this from the graphic point of view. So let's look at more definitions right here. All right, what does Fermat's theorem is going to tell us? So whenever a function f has a local maximum or a local minimum at some value c, in this case, if that derivative is evaluated at those values c, then that derivative will be equals to 0. And that's again because for these values, for example, f of c has a maximum right here. That means the derivative, and by the way, the derivative by definition is the slope of the tangent at that given point. So in this case, this is going to give us a horizontal line. And what's the slope of a horizontal line? 0, right? So we're looking for those values for which the derivative is 0. Those values will potentially be used to determine whether we will have a maximum or whether we do have a minimum for the function. All right. And the algebraic process, well, there's an algebraic process to go about this. Well, all we have to do is take the derivative, set it equal to 0, and solve that equation that we obtained. So all those values that make the derivative 0 or the derivative undefined, those are going to be our critical numbers, which will potentially give us a maximum or a minimum. All right. So, well, this is the same graph. I don't think we need to go about this. So let's find the critical numbers of the following function. So we're not going to graph anything. We're just going to go about the algebraic process for this. All right. Okay. Find the critical numbers. So number one, the first thing we do is take the derivative of this polynomial, f prime of x. And the derivative is 3x squared minus 6x. Alright, so that's the derivative. And from here we set the derivative equal to 0. Because again, the derivative equals the slope of the tangent line. And we are setting up an equation to find those values of x for which that slope will be equal to 0. In other words, 3x squared minus 6x. Set it equal to 0 and solve the polynomial equation in this case. Do whatever you think is doable in this case to solve this polynomial equation. And I think it's factoring the greatest common factor of 3x, x minus 2. So when solving this equation, either 3x equals to 0 or x minus 2 equals to 0. So x equals to 0 or x equals to 2. So those are the two critical values. Which of them is going to be the maximum, which of them is going to be the minimum, we don't care at the moment. But those are the two values of x for which we will potentially have a max or a min, or both, you know. We don't know. Alright, I mean, just so we don't feel like we're just crunching numbers, derivatives, and expressions and all that, how about we verify this graphically? Alright, so that let me graph this function so that's clear. So x cubed is that minus 3x squared plus 1. And let's have a look at the graph. Alright, okay. So let me zoom a little bit. Zoom in a little bit. No, maybe not that much. Zoom standard, and let me do zoom box. All right. Let me create a box around. Okay, I think I need to put enter, yes. Okay, this will cover that. Alright, so we got as critical numbers x equals 0 and x equals to 2. That means those are the values of x for which we will potentially have either a maximum or minimum. Let's verify that. So what do we have for x equals to 0? It's a maximum. What do we have for x equals to 2?
It's a minimum.
It's a minimum. Does that check with our idea as before? Those critical numbers are for sure going to give us either a max or a min. How are we going to determine analytically? Well, that's going to be a section further in the chapter. For now, let's get familiar with how we get this critical values, which potentially gives a max or a min. All right. So x equals to 0 and x equals to 2. Let's look at another one. G of x equals x squared ln of x. So we need to find the derivative and then set that derivative equal to 0 to find those critical numbers. Number one, To find the derivative of this function, any ideas on how to differentiate this one? Which product rule? So let's write down what the product rule is. So product rule, so that's u v prime equals u prime v plus v prime u. Right, that is the derivative of this first function times the second plus the derivative of the second function times the first function. And well, so the derivative of the first function, which is 2x ln x, that's the second function itself, plus the derivative of ln, what's the derivative of ln again? 1 over x times x squared. And again, let me label just so you can see the product rule in action. So that's u prime v and v prime u. Right? That's our product rule in action, which would be a good idea to simplify if we are to solve an equation here. All right? So, well, this is simply 2x ln x plus x. And in this case, we need to set 2x ln x plus x, set it equal to 0 in order to find out what those critical values are. So we need to solve this equation for x. Number one, notice how we have a common factor of x. So that's x times 2 ln of x plus 1 equals to 0. Using the zero product property here, which is not limited to just products of linear factors, it also works with other factors like logarithm, trigonometric, exponential. That means either x equals to 0 or 2 ln x plus 1 equal to 0. Alright? Well, x equals 0, well, it's already x equals to 0. Let's solve 2 ln x plus 1 for x. So subtract 1 to both sides. And ln x equals negative 1/2. And to get x by itself, what do we do? What do we do to solve for x, to get rid of the ln? So we need to exponentiate both sides. Alright? Cancel e with ln. That's going to give us x equals e to the negative 1/2 or 1 over e to the 1/2 or 1 over the square root of e. Either way. So these are our two critical numbers. X equals to 0 and x equals to 1 over the square root of e. Alright. So number one. Okay, let me go back to the graphing calculator so we can visualize it. But first, I would like to get an approximation of this value using the calculator. So that's 1 divided by the square root of e. E is right here. Nope. Second e. So that's approximately 0.6065. Alright, and let's have a look at the graph of the function. The function g of x equals x squared ln x. So I'm going to clear x squared ln of x, and let's graph. Well, in this case, we don't have okay, let me, I think this is a good window to have a look at the function. And well, we need to be very careful with the results that we obtain. Because in some cases, yes, we're doing the correct differentiation, we're using the correct differentiation rules, and when it comes to getting those critical values by setting the derivative equal to 0, yes, we do the correct algebraic techniques, and as you noted in the process we did before, we didn't do anything mathematically illegal. I mean, add 1 to both sides, divide by 2, exponentiate both sides, and then use some properties in this case, right? So, let's verify this number, 0.606. Is that really a critical number? That is that a value that will for which the function will potentially have a maximum or a minimum? Well, see the minimum here? Do you see the value of x? It's likely bigger than 0.5, slightly bigger than a half. So that checks the result graphically. However, what about 0? Is 0 a legitimate critical number? What do you think about this one? Yes.
Is the derivative fine?
Sort of, yes. But that's part. That's what you're saying. It's a consequence of what I'm gonna go through. Well, in this case, did you see graph below x equals to 0? In fact, there's no graph, and that's because, well, in this case, we need to consider the domain of the function. The domain, in this case, well, for x squared is all real numbers. However, the ln of x has restrictions in its domain, isn't it? X cannot be no. Okay, the domain is only x 0 to infinity. In fact, this function excludes the 0 from the domain. And well, yes, even though this x equals 0 pops out of the solving the derivative to get the critical numbers, however, disregard this number because not in the domain. Not in the domain of f of x. So if a point is not in the domain of f of x, it cannot be a maximum or a minimum. So that's the ultimate conclusion here. That's the ultimate result in this case. All right. So we need to be very careful when finding critical numbers. Yes, again, we didn't do anything wrong. We got the derivative, set it equal to 0. We did the zero product property. Everything worked just nice. However, and I did this on purpose of skipping the domain from the very beginning of the problem. And that's something you don't want to do. In fact, that's the first thing you want to do every time you are to find critical numbers and determine maxima and minima, points of inflection, etc. Look at the domain of the original function. Yes?
Yeah, so do we always get maximum and minimum when we do a derivative? Like, can we get minimum, minimum, or maximum?
We can get one of each, or two of each, or only max, only min, depending on the behavior of the function, and also depending on the interval that we're working. For local minimum, we're looking at the entire number line. Well, on the domain, considering the domain restrictions of the given function. However, if, like in this case, we will look at only absolute max or absolute min. In this case, it's going to be restricted to some interval, and depending on the behavior of that interval, we may get one of each, two of each, or depending on the function. All right. Let's do another one. Oh, note. Note. Look at the domain of f of x first. All right, that's the first thing we do, and I did it, and I skipped that part on purpose just so we can. We can go back and check that out. And the reason, or rather the purpose of looking at the domain of the function is to make sure, to determine whether these critical values are legitimate or not. All right? Let's do another one. G of x equals sine squared x minus cosine x. All right, any ideas on how to differentiate this function? What about the first term? How do we differentiate sine of x? Sine squared x, rather. Chain rule. It's a mini chain rule problem, right? If we rewrite sine x quantity squared, which is what this really means, this is, well, 2 times sine x cosine x minus the derivative of cosine, which is negative sine x. All right? Let's simplify this derivative a little bit. I mean, it's just multiplying the sines. 2 sine x cosine x plus sine x. That's g prime. And let's set the derivative equal to 0 to find the critical values. That is 2 sine x cosine x plus sine x. Set that equal to 0. Okay, so this is a trigonometric equation. This type of equations have periodic solution. In other words, this one will have infinitely many solutions. Well, we don't have to write infinitely many solutions. We will have the solution. We will write the solutions in a more condensed format. So number one, let's factor out the sine, and that's 2 cosine plus 1 equals to 0. This means from factoring the sine, so sine x times 1, that's going to bring back the sine here, and sine 2 cosine x is going to give it this 2 cosine sine. So this means a couple of things. Number one, sine x equals to 0, or 2 cosine x plus 1 equals to 0. Well, so for the first equation, I think this one is a good one to represent. Well, so for which angles is the sine function equals to 0? Okay, let's list a couple. 0? Is there another one? 360 or 2 pi? Anything between 0 and 2 pi? Pi? 2 pi? 3 pi? Etc. N pi. Let's call it n pi. Multiples of pi. Alright, for n being an integer. Alright? Then, what about the second equation? So that's 2 cosine x plus 1. That's the same as saying 2 cosine x equals to negative 1, and cosine x equals to negative 1 half. Alright. So we will be looking for all the angles that have a cosine equal to negative 1 half. So number one, I'm going to do a Cartesian plane. All students take calculus, you know that acronym, to determine which quadrants do we have the positive trigonometric function. So in this case, this A means that all trigonometric functions are positive. Here, this S means that sine and its reciprocal cosecant are positive. Everything else is negative. T stands for tangent. That means that tangent and its reciprocal cotangent are the only positive trigonometric functions. Everything else is negative. And on the fourth quadrant, that C stands for cosine, and also its reciprocal, which is secant, are positive, and everything else is negative. So which quadrants, based on this, which quadrants will have a cosine equals to negative in this case? Second and third, right? Second and third. So let me draw a couple of triangles, second and third. So which angle is this for negative 1 half? Oops, no. Negative 1 half. So I believe this one has to be, is that 2 pi over 3? 2 pi over 3 and 5 pi over 3? No, 4 pi over 3, right? 4 pi over 3. So in this case, okay. So what's going to happen with 2 pi over 3? If we go around the circle, we add 2 pi, we're going to get back to the same point, 2 pi over 3 plus 2 pi. Do another turn, that's going to be 2 pi over 3 plus 4 pi. Do another turn, 2 pi over 3 plus 6 pi, and same situation with the 4 pi over 3. Go around the circle once to get to 4 pi over 3 plus 2 pi. Another turn, 4 pi over 3 plus 4 pi, etc. So in this case, we are not going to list all the different possibilities. We are going to list them as number one. Okay, critical values. These are going to be of the form number one, n pi, all right, or 2 pi over 3 plus 2k pi or 2n pi. because essentially we'll be adding multiples of 2 pi to get back to the same point where 2 pi over 3 is. And likewise for that last piece of information, that's 4 pi over 3 plus 2n pi. And that's going to give us the set of critical values. And for example, in this case you can make many cases where n equals to 0, n equals to 0, and n equals to 0. We should get 0, 2 pi over 3, and 4 pi over 3. Those are actually called the principal values when you use the n equals to 0 case. Well, then we start to get generating periodic values, that is n equals 1, n equals 1, n equals 1, you know, and you start just generating infinitely many solutions, not just positive, but actually n is negative. So in this case, n belongs to all the integers, and notice it's all the integers. In some cases you may have seen this notation z plus and z minus. That means all positive integers, all negative integers. In this case, without the subscript or the superscript, in this case, it's all the integers, not just negative, not just positive, all the integers.
Yeah, so we have to include the symbol after.
Just for the sake of formality, just to be known, because n cannot just be anything. It cannot be 0.5, right? We need to make sure that n is either this symbol or just n is an integer, either way. But the fancy z looks better, right? Looks nicer. All right. Alright, let's have a look at what's next. Okay, absolute maximum and absolute minimum. Well, today we're going to go about absolute max and min. We're going to look at one example, the algebraic way to get these abs max and abs min. Well, so here is the procedure to go about those kind of problems. So essentially, find the derivative of the function and then find the critical values of x. So the critical values of x is actually f prime set equal to 0. Those are the values that will potentially be maximum or minimum or nothing in this case, like in the case of the x squared ln x, in which we got an x equal to 0. That was nothing because that value was not in the domain of the original function. So then we're going to make a table of values and evaluate the original function at the endpoints of the interval, the closed interval that we are analyzing the function for, and the critical numbers. So number one, let's have a look. I believe we already did this one, right? F of x equals x cubed minus 6x plus 1. F prime of x equals 3x squared minus 6x, all right? And set the derivative equals to 0. 3x squared minus 6x equal to 0. And well, 3x, x minus 2. Yes, this is the same one we did before. From here, x equals 0 and x equals to 2 were the critical values. So this is what we're going to do. We're going to make a table. And this table will be including x, all the x values, critical values, and the endpoints of the closed interval. In this case, the endpoints were -1/2 and 4. All right. So f of x equals to x cubed minus 6x and plus 1. 6x squared, right? 6x squared plus 1. All right, so this is what we would have to do. Number one, plug in all these values, the critical values, at the original function f of x. That is f of 0. It would be 0 cubed minus 6 times 0 squared plus 1. This reduces to 1. All right. What about f of 2? F of 2 equals to 2 cubed minus 6 times 2 squared plus 1. Okay, let's do one at a time. So 2 cubed, that's 8. And 2 to the second, that's 4. 4 times 6 is 24. So that's 8 minus 24. That's going to give us a 16, negative 16 plus 1, negative 15. All right. What about, okay, these complicated numbers? Okay, so if you have a TI calculator, let me show you how to do this. So you want to go to Window, no, actually Table Set, and have the independent variable to ask. And that's to ask what's the function or what's the value of a particular independent value in this case. And so let me write down the function again. So that's x cubed. X cubed is that minus 6x squared plus 1. And let's go second table. Notice that this table is going to show empty. So I'm going to plug in all the values. 0, 2, negative a half, and 4. So second, 0, entered. We get 1 again, right? And what was the other one, 2? Negative 15. And what's the next one? Negative 1/2. Negative 0.625. And 4, negative 31. All right, so 6.625 and negative 31, negative 0.625 and negative 31. Now from here, looking at the table, we are going to determine and decide rather which value is the maximum and which value is the minimum. Well,
Maximum is 1.
maximum is the largest of the y values will be the maximum, right? So that's going to be our absolute max, and the smallest value of y will be our absolute minimum. Which one is it?
Negative 0.625.
How about negative 31 is even smaller than that?
Oh, because it's low.
Yeah, it's a decimal.
I think it should be negative 3x squared, but that's negative 6x squared.
Negative 6x squared?
It should be negative 3x squared, like 35.
Really? Negative, oh yes, negative 3x squared. Oh, okay, I see what I did. Yes, negative 3x squared. Oh, what the hell. So 3. Okay, that's going to change some of the values. Yes, negative 1, it's still, the first two are still the same, negative 1, negative 3.
So the absolute value is 17.
3, so that's a 3. So that's 0.125 and 17. And that's positive 0.125, 17. So that's going to change a lot. This is the absolute max. And the absolute mean would be the smallest in this case. Oh, that was a 17, right? Or what was that? Negative 3. So that's the absolute mean in this case, right?
And then the rest are local relative maximum.
We don't know what they are, so they're for sure local something. We will need more pieces of information, such as in this case the first derivative test and the second derivative test, which we will discuss later in the chapter. For now, we'll look at the academics. So this is it for today.